Start. Hello, everyone. Welcome to the Topology Optimization webinar. Today is our 26th session. It is kindly organized by Professor Allaire, Professor Amstutz, and Professor Bogosel, all from France. So thank you for organizing today's session. Please take it over, Professor Allaire.
Thank you very much, John. So welcome to everybody. So I was invited to host this webinar, and so the main role of the host is to choose a topic and then the speakers. So we choose a topic that we like. Okay, so I hope that you will like it too. And we choose speakers that are, of course, expert in the topic, but that we like too. So I'm very, very pleased to have the list of the 4 speakers. And let me immediately pass the floor to the first speakers, which are Alicia, Kim, and Andreas, Neofytou. So the floor is yours for 15 minutes. Then we'll have a few minutes of question, and there will be maybe some further discussion at the end after the 4 speakers. So please, Alicia and Andreas, the floor is yours.
Lovely. Thank you very much for the invitation, Allaire, Professor Allaire. And I'm really excited to present our work on level set topology optimization for fluid structure interaction. Andreas Neofytou is my star postdoc who's actually done this work as part of his PhD, currently works for me as a postdoc, and he will sort of take over. But let me introduce sort of the topic and how we approach this subject. So if you go to the next slide, we identify that really the new challenges that people sort of think about in fluid structure interaction can be summarized in these sort of 3 points. One is the fluid structure interface. So we actually need to know exactly where the boundaries are. And in some of the methods that we have, that's not always very clearly identified. And one of the reasons why the interface, clear identification of interface actually is important is that as the structural boundary moves, because we have the fluids, we need to move the pressure with it. So we have a design dependent load. So we actually need, so if we're going to use finite element, for example, we need nodes just at the interface to be able to move, apply the pressure and then move with the boundaries. And then the third thing is that as we move the boundaries, some part of the domain becomes fluid, some part of the domain becomes solids. And how do we apply these 2 different governing equations into this domain? So those are sort of the 3 main challenges. So if you go to the next slide, one of the reasons why we thought that our level set method is a appropriate approach to try to do this problem is because we have a level set method that uses the level set function, which means we always have a clear, well-defined boundaries, and then we use the level set equation to evolve the velocity fields. So then we essentially sort of directly control the interface. So that is that sort of addresses first couple of challenges. It puts us in a good stand to do that. And if we go to the next slide. And we have recently implemented this new architecture. So what I would say that this software architecture is actually one of the enablers. And what we did was to put together the sort of modularization to our topology optimization. So we decouple the state equation solve, which is our standard finite element mesh, and then we decouple the level set grid, which is our design parameters. So our design parameters and our state variables are decoupled, and as long as there's a mapping between the 2, we can actually apply this framework to all topology optimization methods. Also, this means that we don't necessarily have to use finite element method. Any kind of PDE solve on the right-hand side is applicable, and that we can actually map it between the 2. So using this framework, we've developed the fluid structure interaction solver with topology optimization. And I'm going to pass that on to Andreas, who's done all the hard work.
Thanks a lot, and thanks a lot for the introduction. Hello, everyone, from me as well. Let me just. Going back to the second point of the 3 points that we discussed in the second slide, the way we address the design dependency as a start was to bring in a particle approach into our level set method. Specifically, we're using the reproducing kernel particle method, and the idea is that now, instead of having elements with predefined connectivity, we build our shape functions relying entirely on a set of scattered points or particles that do not have any predefined connectivity. So we are free to lay the particles over the domain any way we want. And the idea is that we can lay those on the boundary and exactly track the boundary to address the design dependency. And the idea you see here on the right, basically we lay the particles over the domain and we have these shape functions that now overlap over the domain. As a start, we experimented with the method using stress-based problems. For example, here you see stress minimization for this L-beam on the left. And as I said, since we are free to move to place the particles in any way we want, we got a bit creative here. So what we do is what you see here on the top right corner. Basically, since in the level set method, we're computing sensitivities at the boundary point, so we're mostly concerned with accuracy near the boundary. We chose to lay a more dense particle distribution in a narrow band close to the boundary, and then we keep the particles more sparse in the interior. And what we show here on the top is that basically we can get the same solution even if with this distribution compared to a distribution with very dense particles. So we want to show here that basically the method is not sensitive to the way we lay the particles. And on the bottom, you see how it works for internal boundaries as well, for a case where we start with initial holes in the design. There are additional benefits that come with this reproducing kernel method, and one of them is the fact that it can allow for controllable order of continuity. This is an intrinsic property by construction of the shape functions, so we can easily control the order of continuity without additional complexity, and in our experience, without much additional computational cost. So here, what we have observed for these stress-based problems is that, as you see an example here, as we increase the order of continuity in the shape functions, basically we can smooth the convergence and even get a faster convergence. Now, coming back to the design dependency, here you see an example of how this works in action. So here is an example with purely hydrostatic pressure loads. And the idea is that we start with this design with pressure load on the top. As the design evolves, we expect the pressure loads to change in direction and location such that they follow the loading surface. And you see the action here on the right, basically as the topology evolves, because now we have particles at the interface, so we exactly model the boundary. We can directly apply the loads and track the loading surface. Having addressed the design dependency in this way, we're looking to extend to the more complex case of fluid structure interaction, and we did that by using the modified immersed finite element method. So we've been, this is a very well-known fluid structure interaction approach in the literature. And it has been applied to a wide range of problems. So we have some citations here from our collaborators on this work. So it has been applied for multi-phase flows, high Reynolds numbers, transient problems, large solid deformations. You will find all the details here in the citations. But the key idea of the method is that it basically allows for two separate domains. The fluid part remains fixed on the background, whereas the Lagrangian solid sits on top, floats on top of the fluid, and is free to deform and move. The way the two see each other, so on the fluid side, the way the fluid sees the solid is through an artificial fluid region, as you see here on the bottom left. This artificial fluid region is essentially governed by the same set of equations as the rest of the fluid. It's just that here we basically interpolate the solid properties onto its overlapping fluid region, the region of the fluid beneath it. And we try to make this artificial fluid behave as much as possible as the solid. So now when we solve the entire fluid domain, we have this part that behaves as much as possible as the solid. Now, the way the solid sees the fluid is as an FSI load on the interface. Now, since we have the particles at the interface, we can apply the loads directly at the boundary on the solid side. One of the key elements of the modified immersed finite element method compared to other immersed methods, and where this term modified comes from, is the fact that it solves the solid by its own governing equations. Whereas typically in immersed methods, what is done is that the solid deformation is imposed from the fluid solution. This has been shown to lead to mesh distortions and the solid deformation overestimation, especially for high Reynolds number flows. And an example you see here, this you will find the details in the citation given on the slide. But what is shown here is that basically it's a comparison between MIFM and IFM. We see that for low Reynolds numbers, the deformations are small, but there is a slight overestimation in the case of IFM of the solid deformation. Now the problem is more apparent if you go to higher Reynolds numbers. So as you see here, IFM has this mesh distortion on the top left corner, and it fails to capture the deformation. Whereas MIFM does a better job to capture the deformation there. And actually what is shown on the right is that in the case of IFM, even if we refine the mesh further, the computation runs for a bit longer, but it still never converges to a steady state solution. So MIFM, exactly because it solves the solid using its own governing equation, it better preserves the solid dynamics, and it's able to capture the deformation better, even in high Reynolds number flows. And now we're moving on to the examples. Those of you who have worked with fluid structure interaction topology optimization are probably very familiar with this example here, this setup. It's essentially a beam that is placed inside a flow field with a velocity here on the left side. And the idea is that we're trying to minimize compliance under evolving constraint, and there are simplifications that are happening here. We assume steady state conditions and linear elastic solids, meaning that the solid deformation is small. Of course, this is a simplified problem. We chose this in the spirit of validating the approach through comparison with the literature, but by no means the approach is limited to these simplified cases. For the sensitivity computation, we have developed a discrete adjoint approach, and we combine that with automatic differentiation. So here are some of the typical solutions that we see in the literature, and we wanted to acknowledge that plenty of other authors have examined this example. So now we want to compare the solutions that we get to the existing literature. And the first thing that we see is that basically we have some common features, such as these thin supports in the interior, these thin structural members, in both cases for low and high Reynolds numbers. Then we have this exterior interface here that is more rounded in the case of low Reynolds numbers. And in the case as we increase the Reynolds number in the presence of this negative pressure region here, the interface becomes more flat. So these are features that have been observed by other authors in the literature. And we have also examined a different setup of the same example. So it's the same concept, same assumptions here, but just a different arrangement. And again, by comparing with the literature, we get a lot of features similar to what other authors have gotten. So overall, to sum it up, we have developed an approach for fluid structure interaction problems in topology optimization. We combined our level set method with a particle-based approach for the solid domain, and we used the modified emergent finite element method to do the FSI analysis. We see some key points in this methodology. From the point of the solid, we have the flexibility in laying particles in the domain freely. We have controllable orders of continuity, and this gives us a way to directly address the design dependency. From the fluid structure interaction perspective, we see as a positive the fact that we can have two separate domains. So this allows for modularity in our solvers. So we're free to use any discretization we want for fluid or solid, and any software we want. And then we aimed here for efficiency to avoid remeshing the fluid, and also the solid on top, because it relies on particles, it's again doesn't depend on a mesh. This concludes our work. Thanks again for the invitation, and I would be happy to answer any questions you may have.
Thank you very much for this very nice and short talk, and in time. So we have time for questions. So thank you very much, Andreas and Alicia. Are there any questions? June, yes.
I don't really have a question, but I can also start. Andreas, in this animation, I see the points, they are resampled, and you always have more dense samples close to the boundary. How do you do this?
We use a quadris structure, so we don't it's a structure that it's pretty much the same distribution in every iteration.
I have a question.
Please.
Why do you employ the particles to simulate the structure and not the fluid system? Maybe you said that, but I didn't pay attention to that. Why is not in the other way around?
Yeah, actually both are. So it would be possible to use the particle method for the fluid system as well. The method doesn't limit the discretization techniques. We choose the finite element here because it's more like the FSI approach that we use is well tested and developed using the finite element method for the fluid. So we kept that, but there is no real limitation in the method in using particles in the future.
Okay.
I have one question, please.
Please.
So in your what's exactly your physical model that you solve? So do you take into account both the interactions of the solid on the fluid and the interaction on the fluid on the solid, or is it only one way?
In this specific example, is one way because of the assumption that we have a very small solid deformation, but it is extensible to a two-way coupling, and it's definitely in the goals for the future extension of this work.
Okay, thanks.
Thanks a lot.
Any further questions? Well, if not for the moment, thank you again, Andreas and Alicia. So we cannot upload. Well, we can try, but it's not that good. And so we pass to the next speaker. Yeah, you are here, Augusto. So you can share your screen, and you have 50 minutes to explain. There was a question, maybe. No. This was on Camaria who find. Yeah, we can wave hands. Yes, that's right. Augusto, the floor is yours. Thank you.
Well, good afternoon to everyone. Thank you again for having me here. So my work as a PhD student consisted on developing all the necessary techniques in order to obtain optimum designs of thermo-electro-mechanical devices employing topological derivatives. Multiphysics devices are everywhere. We can find cool applications such as piezoelectric actuators and sensors, Peltier modules, and even MEMS devices. The main advantage of these devices is that they can be very precise and then can be very compact at the same time. But designing them can be a very challenging task due to the complexity of their working principle. So in this regard, we want to create tools to alleviate the designer's workload, and we think that topology optimization fits well as a solution for this problem. Since the application of TIM devices can be a very broad area, we will narrow it and focus only on TEM actuators. So what I want to talk about in this presentation is first give an introduction of the theoretical framework for designing TEM actuators. And then, since we employ topological derivatives to guide the topology optimization process, I want to discuss its derivation and calculation for the problem at hand. And then I will give some comments about how scaling optimization has benefits and why is it beneficial, particularly for multiphysics problems. And of course, I will give finally some examples. A TEM actuator works as following. First, you have a conductive and compliant structure. an electrical current will flow between the electrical ports. This electrical current will generate a heat due to Joule effect, and this heat will modify the temperature distribution of the structure, causing it to deform. So the main objective here is to obtain the optimum topology of this compliant structure, and such that the displacement of some portion of it gets maximized in a particular direction, employing a given amount of material. So this is the PDE system that governs the response of the actuator. And the first one is an electrical equation, the second one is the thermal, and the third one is a mechanical equation. This set of PDE is a nonlinear one due to the nonlinear term due to Joule effect. And the thing is, although this system is nonlinear, you don't have to use a nonlinear solver to solve it, because it can be solved in a sequential manner. So this kind of PDE coupling is also known as weakly coupled PDE. Now consider a design domain and a cost functional defined on it. And then what we are going to do is to introduce a perturbation which will be filled with different material properties than the design domain. At what we want to do is to express the perturbed functional in terms of the unperturbed functional. We can do it by means of the topological asymptotic expansion, on which the first term will contain the so-called topological derivative. We calculate the topological derivative of this problem employing Lagrangian techniques. On this paper, you can look for a brief review of the most novel techniques in order to do that. But for this particular case, we will employ the Amstutz methods with some minor modifications. What we were going to do is to express the variation of the cost functional in terms of the Lagrangian function. This first term will be expressed as with a Taylor expansion series up to the second order term. This first term will get canceled out, and this second term will vanish due to the optimality condition of the system. And now we show that this expansion is good enough to calculate the topological derivative of the problem, since we can prove that this remainder has this following estimate. Expressing this first variation in terms of an integral over the perturbation, it's pretty straightforward. But the second term is hard to work with, but we could do it employing the generalized divergence theorem and the boundary conditions of the system, and obtaining this structure. Now, what has left to do is to express these perturbed variables in terms of on the unperturbed variables. We can do it by means of the this asymptotic expansion. This particular one is very known in the literature, is very common, and it is composed of the unperturbed state variables, a boundary layer corrector or exterior solution, and a remainder solution. The main feature of the exterior solution is that they must decay at infinity, and the remainder of the solutions must have this following estimate. Finally, for our design problem, since the cost functional is linear and does not depend directly on the material distribution property, these two contributions will be zero, and then the topological derivative can be expressed in this way by means of the also well-known polarization tensors. What has left to talk about in this presentation is how scaling the optimization problem is beneficial if we employ topology optimization as a design tool. when we work with multiphysics problems, new parameters will arise in the state equations, and we start to lose track on how those parameters and their values will impact the solution of the optimization problem. In order to explain myself, I will use the following example. Suppose that you want to build a TEM actuator and fit it inside this design domain with these boundary conditions. But you also want to know if the optimum topology will be different if you vary the value of the voltage applied on this region. And maybe you're wondering if whether or not the nonlinearity affects on the final solution of the problem. So for this particular case, the state equations are this one. And we replace the cost functional for the augmented Lagrangian one in order to consider the volume fraction constraints. Then we proceed to introduce the following transformation for the independent variables and for the dependent variables and select these scale parameters. And finally, obtain the scale version of the state equation system. As you can see, now these state equations depends only on a set of adimensional parameters that are depicted here in red. Then we introduce the same transformation to the variables here in the Lagrangian and obtain this structure. So now, if we find a minimizer of this functional that meets and the constraints are met, then these terms will vanish. And since the multiplication of a function by its a positive scalar doesn't affect the minimizer of its function, then this term will get canceled out. So in other words, what we can state is that the minimizer of the scale Lagrangian, augmented Lagrangian, and the not scale Lagrangian are the same. So we can now evaluate the impact of the physical parameters in the optimization solution just by looking at the scale version of the problem. And as we can see, none of these adimensional parameters are playing a role in this set of in this problem. Thus, whatever value you select, it will not have any impact on the optimization solution. In other words, the minimizer will be independent of this condition, and this is what I will show in the following numerical slides. So very briefly, to numerically solve the optimization problem, we employ level sets as a domain representation method. To evolve these level set functions, I will employ the topological derivative, and to consider the volume constraints, I will employ the augmented Lagrangian algorithm. Here we present 3 results for these 3 evaluation cases, considering 0.3, 0.6, and 0.9 volts on the applied voltage on this region. And the black zones represent the topology of the compliance structure of the actuator, and the red lines represent the electric field lines on which the electrical current will flow following those lines. We see that, as we expected, that the obtained displacement varies quadratically with the applied voltage. As we expected, this is a result of a nonlinear behavior. And we can see that the topology for all these 3 cases, it's exactly the same. So we numerically see that the optimum topology does not depend on this value. Here, the deformed configuration of the actuator is plotted together with the heat map, which shows the temperature distribution over the actuator. We can see that for the employed heat transfer model, extremely high temperatures are reached. And then we also perform some other studies like parameter sweep on the volume fraction and obtain these results. We evaluate the cost functional versus the volume fraction and also the parasitic movements. But I think that I will skip these examples in order to save some time. So in conclusion, in this work, we presented the optimum tools for obtaining we presented the minimum tools that that are necessary to obtain TEM actuators employing topological derivatives. The major workload relies on the finding the appropriate structure of the exterior and the remainder problems, and also estimating the reminders. Also, we have to consider the increasing complexity of this job as we continue adding more fields to the problem. For this particular case, these sets of problems have to be constructed. And we have to consider that for each one of those problems, there exists an adjoint version of it. So I think, okay. So I think this issue must be addressed in the near future. Also, we saw that scaling the optimization problems gives us tools to gain insight of how the physical parameters are related to the obtained solutions, and we think that possible future lines of work will be applying a technological and performance constraint, and with also more realistic heat transfer models in order to obtain ready-to-build designs. So thanks for having me. This is the end of my presentation.
Thank you very much, Augusto, and you are on time again. Well, both the first speakers were very good for staying on time. So we have time for questions. Who wants to start with the questions?
May I go, Ahmed?
Sure.
So thank you, Augusto, for your presentation. I think in the earlier slides, you said that there was a nonlinear term in one of your.
Yes, I'm sorry. Maybe I jumped. I jumped very fast on the presentation. I didn't mention that.
Yes, just I wanted to. What is the nature of nonlinearity and how you are dealing without solving iteratively? You said that you are using
yes.
a method, I think.
Yes, the non-linear term comes from this heat term due to Joule effects. This load is it can be calculated as this. The non-linearity comes from it will be the square of the norm 2 of this gradient vector. And it is not necessary to solve it iteratively, and the method to solve it is sequentially, because first you solve this equation for the electrical potential field, yes, and then you introduce it, calculate this term, and then you have a linear problem.
Yes, I got it.
And then you move on and solve the next equation. It is a nonlinear problem because it doesn't match the linear properties of a problem, but it can be solved by a linear solver.
Okay, thank you very much. I appreciate that.
Okay.
Thank you. Any other question?
I have a question.
Yes, please.
So thank you for a very nice talk. So not being a mathematician, it seems a bit scary going into topological derivatives. So my question here would be, let's say that you would like to impose a length scale control in this setting.
A what? Sorry?
So I'm saying when you look at the designs later on in your presentation, you can see that you have some very small hinge-like structures.
Yes.
Say that you want to put a minimum length scale on the design. How easy would that be with respect to all this fancy mathematics
This for me, this problem is very hard to solve. I think that a practical solution will be impose stress constraints on the problem. That's the first thing I will try to do. But I think that length scale with topological derivatives have never been addressed yet.
Yep.
So I think that the geometrical problems, geometrical related problems with topology are pretty hard to work with topological derivatives. As far as I know, it follows this complexity.
Great. Yeah. Okay, I think I would assume that you could somehow put it into your design representation, but maybe somebody with more insight into these problems could answer that question then.
Yes,
Thank you
I'm
anyways,
I'm sure that Samuel or Gregor maybe had an answer to this.
Yes, we together with Samuel, we just discussed, I mean, maybe adding the perimeter, because the perimeter can be handled by topological gradient by some recent work of Samuel and some of his colleagues. But that's right, that if you have a more complex length scale constraint, that will be more difficult. But for the perimeter, there are some hope too. And then, of course, adding a perimeter will give you an implicit length scale that you can monitor in some sense.
Okay. Thank you very much.
But by the way, I have a question for Augusto. Okay. So it's not completely clear if you can show us again the scale PDE that it's independent of the magnitude of the imposed voltage.
Yes, the scale PDE.
Yes.
Here.
Yes.
So the adimensional parameters are the contrast parameters here, right. Gammas. Yes. And the other adimensional parameters are these P1 and P2. You can see that this first one is the contrast of the Lamé parameters.
Yeah.
And this P2 is only the stiffness of the stiffness value of that models the stiffness of the workload piece. Length L is an length scale, and again mu is the Lamé parameter. So and phi sub c is this value associated with the parameter associated with the applied voltage, and you can see that it doesn't appear in any of the equation, and even in the augmented Lagrangian.
All right.
So it's independent. If whatever the value you select, it will not have any impact on the solution.
Okay, thank you. Thank you very much for this answer. Any other question? Well, if not, thank you again, and we will have a final discussion. So if there are any other further questions, we can come up. But let's move to the third.
Thanks again to you.
Who is Peter Gangl, so from Linz, and not anymore Graz, so still in Austria. So the floor is yours, Peter.
Thank you very much. And thank you very much for the invitation to present my work here. So this work is about multi-material topology optimization of electric machines, also based on topological derivatives. So there will be some connections to the previous talk. Yeah. And I want to point out that this is joint work with my PhD student Neofytou, and is funded by the Austrian Science Fund. So basically, the talk today will be an application of the two methods in the two papers that I wrote in the abstract to the design optimization of an electric machine. So these two papers are not about machine optimization, but it's about a multi-material level set algorithm, similar to the one used in the previous talk. And the second paper is about the sensitivity analysis in an automated and systematic way for also linear and nonlinear problems. And we want to use it in order to design the rotor of an electric machine. So electric machines can often be modeled in two space dimensions. And the two-dimensional cross-section, for instance, looks like this. It consists of some ferromagnetic material in red here, some air regions in blue. Then we have some coil regions where copper wires are present, and we have electric current induced. And then we have the inner part, which is called the rotor, which is typically rotating. And this typically also consists of iron, air, and possibly some permanent magnets. We want to optimize the geometry in there today. So let me introduce the problem in more detail. We choose to maximize the torque of the machine. And for now, we just restrict ourselves to having one fixed rotor position, but in general, one should look at different rotor positions and maximize the average torque, not just the torque for one rotor position. But this can be done in a simple extension. So the torque can be computed as a function of the magnetic flux density B. And in this two-dimensional magnetostatic setting, the B field can be represented by a single scalar function U, where this magnetic vector potential ansatz B is the curl of 0, 0, U. So the torque depends on U, and U is the solution to this nonlinear PDE, which comes from Maxwell's equations. On the right-hand side, we have the sources, which comprise the electric currents, the compressed current density in the coils, and also the permanent magnetization, M, which is present only in the magnets. And you can already see that the magnets are magnetized in given directions. This we have to take into account when doing optimization with respect to magnets as well. So also note that this is a quasi-linear PDE, so the diffusion coefficient nu, which is the magnetic relativity, depends in a nonlinear way on the B field, which is the absolute value of the gradient of U, which makes sensitivity analysis quite a bit more complicated. And we also have a bound on the maximum allowed volume of the permanent magnets, because magnets are typically expensive. And that's the problem we want to address. We want to optimize the material distribution in the center. And okay, how do we deal with this magnetization direction? So one way would be to include the magnetization direction as an additional optimization variable. But the other way that we will follow is that we prescribe given allowed magnetization directions and then treat every magnetization direction as a separate material. So if we allow for 8 different directions, we end up with a multi-material topology optimization problem with 10 materials, iron, air, and 8 magnet directions. And this is what we want to address today. Okay, so we want to do this by means of a multi-material level set algorithm based on the topological derivative. We already saw what the topological derivative is, so I can be a little bit quicker on this. I used a slightly different notation, which can be extended to the multi-material case. So the topological derivative basically just measures the sensitivity of a cost function J that depends on a material distribution if this material distribution is perturbed at a fixed point x0. So if we introduce this inclusion, I call it omega epsilon, which is just centered at the point x0, has radius epsilon, and its shape is given by what I denote by little omega, but for us it will be just a unit ball, the little omegas. It will always be a ball-shaped inclusion. Okay, so we take it away from omega 1 and give it and add it to omega 2. And of course, we can do the same thing, taking away from omega 2 and adding it to omega 1. We will denote that by T12 and T21, respectively. Okay, and we want to do optimization by means of a level set algorithm. So it's, I think, the same algorithm that Augusto used in the previous talk. It was introduced by Samuel Amstutz and co-worker in 2006. And the idea is, very briefly, to represent a design consisting of 2 materials by means of a scalar level set function psi that maps from your computational domain D into the real numbers. And whenever psi is positive, you're in one domain. Whenever psi is negative, you're in the other domain. And the idea of the algorithm is to define something that we call the generalized topological derivative, which is just T12 in one subdomain and negative T21 in the other subdomain. This minus sign is important here. And if you have defined this, then you can just get your next update as a combination of the current update, current level set function, and a scaled version of this generalized topological derivative. You can run this until some optimality condition is satisfied, which is related to the angle between the level set function and the generalized topological derivative. Okay, so far so good. We want to extend it to multiple materials now. For that, let me first introduce the notation Tij for I and j between 1 and m, where capital M is the number of materials we have. So for instance, I think it's quite clear how it is defined. T51, for instance, is illustrated here. We take away from omega 5 and add it to this blue color omega 1, and we compute the sensitivity for this perturbation as epsilon goes to 0. Okay, so it's quite straightforward to define topological derivatives in this multi-material setting. How can we define level set functions, and how can we represent a design consisting of, say, m materials in a level set setting? Here the idea is to introduce a vector valued level set function psi, so not a scalar function, but a function that maps into Rm-1. So if we want to represent m materials, we have a level set function that has m-1 components. And then to say that my point x is in omega I if and only if psi of x is in the sector Si in this right picture here. So this is the picture for 3 materials. And the nice and important feature here is that every sector has a boundary with every other sector. So every material is neighboring to every other material. This is a nice feature of using this method. Okay, we can define in a similar way a generalized topological derivative. I will not go into detail. It will just involve all different kinds of topological derivative between any 2 materials, and it will involve the normal vectors of these rays or of these hyperplanes defining my sectors. So this NL is the matrix that consists of all the normal vectors pointing into the sector SL. If you define the generalized topological derivative like this, you can run the same algorithm, you obtain the same optimality condition and the same descent behavior of the level set algorithm as the one in the scalar case, in the 2 material case. This was published in this paper, and later on it was actually improved a little bit in order to account for perfect symmetry, also in higher dimensions. On the one hand, in this paper from Japan, which is written in Japanese, and I could only guess what is written in there, but also my master student did it in his master thesis. Okay, so we will use the improved version of the algorithm here. Okay, so in order to run this algorithm, we still need all different combinations of topological derivatives. Topological derivatives are somehow understood for a large class of linear problems. There exist closed form solutions for closed form formulas for topological derivatives, switching from one linear material to the other. However, things get really unpleasant as soon as nonlinearity is involved, and even more as soon as we have a quasi-linear PDE, where the principal part is nonlinear. And this is the case for us due to this nonlinearity in the ferromagnetic material. Yeah, here in this second paper I advertised, we showed a systematic way of computing topological derivatives for linear and nonlinear problems. And that this formula for the topological derivative always involves a first order corrector term. I also saw this in Augusto's talk before. It was called W before. Here it's called K. It's the first order corrector term of when the state is perturbed. So it's related to the difference of the perturbed and the unperturbed state after rescaling, and it is defined as the solution to an exterior problem, possibly nonlinear if you have a nonlinear if you have a quasi-linear PDE. Yeah. So for any two materials, this would have to be solved. So first question is, how can we solve it? It's a problem on the unbounded domain. We solve it by approximating the unbounded domain by a large but bounded domain, and using just finite elements. And this is motivated and justified by the fact that we know some decay behavior of the solution K towards infinity. Okay, and then still we would have to solve this nonlinear problem for every point Z where we want to evaluate the topological derivative. But luckily, in this example for this particular nonlinearity, we can use some pre-computation. We just pre-compute this problem for two parameters in 2 dimensions. We sample it, we do it offline, and then just interpolate this data online, so the optimization can be done efficiently again. This we already did together with Samuel Amstutz in 2019 in this paper for magnetostatics, and here we extended it to a more general class of problems. Okay, so finally I can combine these 2 ingredients and show you some optimization results for our electric machine. We want to optimize the rotor with respect to, as I said, 10 materials, iron, air, and 8 different magnetization directions. We have a bound on the volume for, say, 5, 10, and 15% allowed magnet volume. We use some periodicity conditions here to reduce the computational domain to just a quarter. And here we can see some optimization results for 5%, 10%, and 15% magnet volume of the inner circle. And yeah, you can see it's an interesting tool. We get designs that are often not expected by practitioners and by experts. And yeah, of course, there has to be done some more work. For instance, also accounting for mechanical stability is important. This is not included yet. We didn't include a length scale. And yeah. Okay. And to be more precise, I should actually show this picture. So I want to say that the interfaces are not really crisp, but we do linear interpolation in the elements that are cut by the interfaces. Yeah, right. And here we can see the fields. So the colors denote the solution U, so the third component of the magnetic vector potential, which is not physical, but the isolines of U, which is physical, of course. Okay, so finally, this was only an application including one physics. We're not there yet to include the temperature and mechanical equation, but so we'll just give a brief outlook what is happening next. Actually, in electric machines, it is very important to account for multiphysical effects because, for instance, we neglected, so far we just considered this first equation and neglected this time derivative, which is related to the eddy current losses. These losses actually serve as a heat source. So we should couple it with a thermal equation, a heat equation, because the temperature has a large impact on some of the material parameters. So this should actually be done, and this is one of the next steps we wanted to do. And also mechanical stability, as I mentioned, should be included. And what's a bit challenging in the coupling of these two equations is that they are living on different time scales. The electromagnetic properties are moving much faster than the thermal field. And yes, we have different time scales. And the idea we want to follow for now is to consider the electromagnetic problem in a periodic setting using a space-time finite element method. So that's a different topic, but basically it just means that you, instead of solving a sequence of two-dimensional problems, you solve one three-dimensional problem where the time is the third dimension. Here you can see a space-time geometry and a space-time mesh for an electric machine. It has certain advantages. You can use adaptivity and parallelization also in space-time, not only in space. Movement is captured by the mesh already, so that it's easier to treat movement. And also the incorporation of these periodicity conditions is quite straightforward in a space-time setting. We have done some first optimization results for the eddy current problem, not yet accounting for the heat equation, but the idea is to couple space-time finite element methods for the eddy current problem with a time-stepping scheme for the heat equation. Okay, that's all. Thank you very much for your attention.
Thank you very much, Peter, and you're on time again. Thank you.
Okay.
Are there any questions?
I have a question, Grégoire.
Yes, maybe Martin first and then Niels.
I just applauded. There was an applaud, I think.
Okay, this was applauding. Okay.
I was aiming to applaud.
Okay, just
not to raise my hand. So,
okay, good.
Niels.
So Niels, you can ask a question.
Thank you very much, Peter, for the presentation. So I'm really curious because I find this very fascinating, this problem that you described at the very end about the different timescales, because you meet that in so many applications. So, and maybe my question is a bit primitive, but could you please explain why is this something where space-time would be extra suitable? I'm not sure I get the drift here.
You don't need to do it, of course. It's suitable because it's useful because you can use parallelization in a more heavy way. So it's more straightforward to use parallelization also in time. So there exist other parallel in time methods, of course, but yeah, we found it need to, in order to do parallelization on the one hand, and also the incorporation of time periodic conditions was quite straightforward.
Okay.
Yeah, I guess that's mostly for time periodic boundary condition, no?
Yes.
I would say so.
Mm.
Thank you very much.
But by the way, I have a question about your results on the volume fraction. You impose the volume fraction only on the magnets, and the
Yes.
iron was not constrained at all?
Was not constrained at all. You don't need to constrain it because having
so you
all
don't
material is a very bad design.
All right.
Because as you can see here, the iron guides the flux, and if we have all iron, then we cannot guide the flux in a good way.
All right. Interesting. Thank you. Any other questions?
Yes, maybe just one on this slide. So the red is iron, right?
Mm-hmm.
And so it's like the green parts. Is it like a checkerboard, or is it really you see these tiny triangles which are in the green part?
These are just arrows indicating the direction of the.
Okay.
Sorry. Okay.
Okay. I was confused. Yeah. Okay. Sorry.
No checkerboards. We have magnet pointing upwards here, and the magnet pointing 45 degrees here. This is not iron. Yeah. Sorry.
By the way, Peter, don't you expect that because you have just one position of the rotor, when you will have many positions and then you will do the optimization of the average, probably the solution, the design will be much smoother now? Don't you expect that?
Yes. That can be. Yeah, so this design is rather smooth, I would say, but.
Well, maybe I did not express myself correctly. Smooth, maybe more regular in some sense. You see.
Yes, that's for sure.
You know, you have many small bars. Maybe you have less. I mean, that's my intuition, but maybe my intuition is not correct, huh?
Mm-hmm.
Yes, there is a question by Filippo. Filippo, please.
Sorry. Okay. Yes. Thank you very much, Peter. Yeah. Jumping off the remark of Professor Allaire, have you just tried to see how sensitive is the position of the rotor, like of this architecture? If you shift it by like some degrees, how bad does it get?
Yeah, we tried few different rotor positions and we get different designs, but I didn't check for just tiny changes.
So my question is, once you have a geometry, if you shift that geometry by like an angle theta, how bad does it? How rapidly does it shift from being optimal to being not very optimal? That was the like. Is it easy to handle?
I haven't done enough experiments to answer that question, I think, but
okay.
Yeah, no, sorry.
Okay, thank you.
Okay, so maybe I guess it is time to go to the next and last speaker, Florian, and then we will have a discussion after that. Excellent. So 50 minutes for you, Florian.
Sorry, I'm using two screens and I have difficulties, but now it's okay.
Well, we don't see your slides for the moment.
Okay, and I put full screen. Okay, is it? Do you see my?
Yes.
My slide.
You also see myself, so you should.
Okay.
Yeah, good, excellent. That's perfect.
Okay. So thanks, Grégoire, for the invitation. So I'm going to present my work on parallel body-fitted three-dimensional topology optimization of multiphysics systems. So it was a work that I did as a PhD student under the supervision of Grégoire Allaire and Charles Daponi as a CIFRE PhD student with some colleagues also at Safran, Julien Cortial and Felipe Bordeaux. So everything that I will present in this presentation is given in full details in these two publications. So the outline of this talk will be a bit. So I will start by giving an overview on the multiphysics models that I've considered, and then I will describe the three main ingredients regarding the numerical methodology to achieve topology optimization with a body-fitted remeshing method. And then I will show you some three-dimensional test cases. So we have a domain which is constituted of a fluid part and a solid part, and this also can account for situations where there is no fluid or no solid, where there is only one of them. And we consider three physics. The first physics that we consider are the Navier-Stokes equations. So we have a fluid that is flowing through the fluid part that is described by the nonlinear Navier-Stokes equations. And once you have solved for the fluid, you can solve for steady-state convection diffusion in the fluid and both the solid part. So in the fluid, you have the convection and diffusion of a temperature field. And in the solid part, you have only diffusion, and both temperature are coupled by the equality of temperature and heat flux at the interface. And once you have a temperature field and a velocity field, you can consider linearized thermoelasticity with fluid structure interaction, meaning so you assume that the displacement of the structure will be small, and given the fluid velocity, you can impose the continuity of normal stress at the interface, which means that the solid structure receives the pressure from the fluid. And also you can account for the temperature field that exists in the solid part, and this is how you take into account also the thermal dilation. So this is a weakly coupled model we solve these equations in a cascade, and there is no coupling back from the solid to the fluid, which was also related to the questions that I asked to the first speaker. So now the numerical methodology. So we use the method of shape derivatives, so the so-called Hadamard boundary variation method, where we seek deformations of the interface that will minimize some objective function, can also take into account constraints. And we do this by considering vector field perturbations. So we consider a small vector field theta, according to which we deform the interface. And and we can compute some asymptotic expansions of the objective function on the deformed domain like this, and the linear variation with respect to the vector field is called the shape derivative. So first part of the work was to compute the shape derivative for these three physics problems. So for an arbitrary, so it's an ugly formula, but the idea is that for an arbitrary objective function that depends on the geometry and on the state variables, you have a generic formula that you can implement in the computer. And this generic formula involves some partial derivative, and as well as three terms that corresponds to each of the physics, as well, and they also depend on adjoint variables that are solved in a reverse cascade. Okay, so using this shape derivative, we can use gradient algorithms, and but this gradient algorithm will require a methodology to update the shapes. So in order to take into account the various physics and to enforce the physics exactly at the interface, we use body-fitted meshes, following an idea that was presented in a paper from Allaire and co-authors in 2014. So we have an exact mesh description of the fluid domain and the solid domain, and the interface is exactly captured, so we solve directly the physical models without interpolation. We remesh with the open source library MMG, and so the algorithm works like this. So if we have a descent direction which is represented by a vector field on the mesh, we start by computing a level set whose zero ISO value matches exactly the interface of the fluid and the solid region. We advect this level set on this computational mesh by solving the advection equation, and now we know implicitly the new domain. We can break the zero isoline of the level set by using. So this is achieved automatically in the MMG library, and then once we know the new domain, we can remesh to improve the quality of the finite element mesh, and we get as thus a new mesh. And also, so this methodology takes into account possible topological dramatic topological changes, such as all collisions of boundaries. One advantages of this body-fitted method is that it allows to capture very fine details. So this was one example of the classical cantilever structure that we optimized with this method, and this is a cut representation, and you see that we can obtain a structure with plate-like structures for which the thickness of the plate is not bigger than two tetrahedrons. So we by using this body-fitted method, we can capture fine structures with a high accuracy. Okay, so the second ingredient of this methodology is the null space algorithm. So in order to take into account generic constraints, so we implemented our own algorithms. So we wanted in general to be able to solve with the level set method arbitrary optimization problem with equality constraints and inequality constraints. So let's say that we have P and Q inequality, P inequality and Q inequality constraints. And in order to take into account some specificities of the level set method, I was not satisfied with the usual augmented Lagrangian methods for the test case that will follow. And so we proposed we devised this algorithm, which is very convenient because we don't need to tune too many parameters to make it work. So we solve an ODE. So the design variable is called X, but so it can adapt to the setting of the level set method or the body fitted method. And we have to compute two descent directions. One descent direction is called psi j. It minimizes the objective function while taking into account the constraints. And the other direction is called psi c, is the range space step. And it takes into account, it reduces the violation of the constraints. So basically, psi j is a projection of the gradient on some tangent space of the constraints, and psi c is like a Gauss-Newton direction for minimizing the violation of the constraints. So I will not go into too much into the details, but the idea is that, okay, so this, okay. So this is what the algorithm does. So it follows when no constraint is active, it follows the gradient. And when some constraints become active, it decides if it's good to move tangentially or to escape the constraints to go back into the feasible domain. I will stay like this because I have other small animations. So we applied this to be able to deal with arbitrary constraints. And so the last ingredient was parallel computing. So for 3D applications, so in order to achieve large-scale computation somehow, we needed this domain decomposition methods. So we relied on the finite element discretization and Newton scheme for the Navier-Stokes problem. And so all the finite element operations were achieved in parallel using PET-C and the interface with preframe that has been provided by Pierre Jolivet. And by doing so, we were able to perform computation on meshes up to 5 million tetrahedra with 30 CPUs. So we used physics-based preconditioners, so geometric algebraic multigrid with the conjugate gradient methods for linear elasticity. We used the hypersolver for thermal conduction and convection, and we used a quite recent augmented Lagrangian preconditioner for the linearized Navier-Stokes, or the so-called OSIN problem for solving the Navier-Stokes equation and also the adjoint of the Navier-Stokes equation. All right, so with these three ingredients at hand, we are able to solve a variety of test cases. The first example is a test case where there is only fluid involved, which is the classical but not so often treated with topology optimization tools lift drag problem of a flying obstacle. So we maximize the lift, which is the vertical force generated by an obstacle, subject to a constraint on the drag and also a volume constraint. And we also require that the flying obstacle has his center of mass is in the middle of the design domain. And we are able to obtain some quite natural aerodynamic structure, which is reminiscent from airfoils. All right. So the second test case was a fluid structure interaction test cases, which is the 3D counterpart of what was presented in I think it was the second presentation. So we have an incoming flow coming in the left-hand side of the domain, which pushes against a vertical obstacle. And we want to find the distribution of mass that minimizes the compliance subject to some volume constraints with this fixed, so this plate is a non-optimizable region. And also, so we did this in 3D, so we had to devise an initialization, and so the optimized shape looked like this. It was quite intensive computation with approximate 2 million of elements, and this is what looks like this optimized shape. So you see also one of the advantages of the body fitted approach is that with MMG we could prescribe small elements on the fluid structure interface, but larger elements as we were further away in the domain. All right, and you see the elastic deformation. So then we also consider the 3D convective heat transfer problem, where we maximize. So this objective function corresponds to the heat that is transferred from the left-hand side to the right-hand side. So we have an inlet and an outlet, and on the red stripe we apply constant heat flux. We apply a constant temperature, which is larger than the inlet temperature, and we also prescribe a maximum pressure drop for the efficiency of the heat transfer, and also a volume constraint, although it would not, strictly speaking, not be necessary. And so this is the initial domain, and as the optimization goes, we see the arising of some fluid channels, and a final structure is obtained, which looks like this. And we also see some part of the design which are whose interpretation. So this small sheet structure are preventing our insulating part, which presents the cold part of the channels to affect the hot parts. All right, and the last example, which was the most intensive one, was fluid-to-fluid heat exchangers. So we have two fluids, one cold, one hot, and the objective was to maximize the heat transfer between the two fluids. And the difficult part of the problem was to enforce a non-penetration constraint, which means, which we decided to enforce by imposing a minimum distance between the two channels. And so this was possible also because of the explicit description of the fluid and the solid region. So we wrote the optimization problem, and we devised a method to do this. So I will not explain here, but basically, so we managed to implement this in 3D using large elements. We had also to devise a nice initialization, and so it also worked, and we obtained highly resolved three-dimensional fluid-to-fluid heat exchangers that respect the non-penetration constraint. And so here is a look of the structure. And so with that, this is the end of my talk, and I think I am on time.
Yes, thank you very much, Florian. And the floor is open to any questions. Yes, Martin.
Yes, you said that you were able to do some kind of mesh adaptation or something. Is that so? Could you handle sort of finer mesh in the boundary layer and so on? And how did you do that?
Yes. So in fact, so with MMG, the library MMG, okay, you can prescribe a maximum edge size on some boundaries. So you can and also the gradation of the edge size. So you can really tune the edge size on different boundaries and say that you want some fine edge size on the inlet or on the outlet to capture boundary layers, or also at the interface between two domains in order to have a very good approximation of the boundary, but also larger elements in the more homogeneous part of the domain.
But since the topology changes and everything, do you have to sort of could you give fixed parameters for that, or do you?
Yes. You give parameters to the remeshing the remeshing tools. That at every iteration you remesh your structure, and at every iteration, so the MMG library will impose the edge size that you want on different boundaries of the domain, which are represented by fixed numbers.
Okay.
Yes, so I guess there were also questions. Natasha, maybe?
Thank you. So my question is back to the one that you asked, actually, Florian, earlier, about the two-way coupling. And can you talk about some of the challenges of two-way coupling and how you want to, or how you handle that.
So how I am on. So I don't understand if your question is about the future work or if it is on this work.
I think you said that you are one-way coupling right now.
Yes.
But
yeah.
it's also work that maybe you have continued since your thesis, and how you're thinking about it, or how you would think about it.
So right now I've not worked yet on the two-way coupling, but it's much more challenging because the coupling from the fluid to from the solid to the fluid would involve the nonlinearities with the deformation of the fluid. You have to transport the fluid variable in the deformed configuration, or the solid variable in the deformed configuration, and this imposes nonlinearities which can be difficult to treat. I know that there is an extension of a fluid structure models that is linear and that could be maybe taken into account. I don't remember the author, but so there are current also there is at least one alternative model which is fully linear, which is non-linear, but which could work because you manage to bring the fluid and the solid, the deformed solid configuration inside a fixed reference configuration, and you can then work on that. But I mean, this would need definitely reconsidering the physical model.
Thank you.
You, Ahmad, you were asking.
Thank you. Thank you for a very nice presentation. I have a couple of questions. First question, I'm following with the Martin question regarding your remeshing. When you are remeshing, you are mapping your old finite element space to a new discretized domain. Could you make some comment what will be the error propagate from this mapping? How accurate it is? Or have you considered using, I don't know, XFEM, GFEM, one that you don't know, you don't need this remeshing?
Okay, so I think, so is your question related to this, so why we choose an optimized then discretized approach and not the discretized then optimized? Is that
No, it is not my question. My question is when you are remeshing, so, yes. So you have a domain that you are doing all of your analysis.
Yes.
And then when your topology gives you a new geometry, you are remeshing your domain. So you have to map from your old analysis, even sensitive analysis, to the new one. So in this mapping, you will have some error, yes? Because it is some approximation. Could you make some comment on this? How?
I mean, at least from the implementation point of view, we don't work with such a mapping. We at every iteration, we have a body fitted mesh at hand, and we compute the state variables, we compute sensitivity variables, which are defined on the mesh, and from that we can compute the shape derivatives on this mesh, and then we identify the descent direction, which is a vector field defined on this mesh. So then we update the boundaries and we get a new mesh, but there is no need of any mapping between the mesh at iteration n and the one at iteration n+1.
So you deform the mesh. It's not remeshing. It's mesh deformation,
no,
or
it's I say it's an abuse of language. We remesh, but it's really this picture in my presentation where we have a body fitted mesh, then we compute this level set, and then we remesh. And we get this new mesh.
Okay. And my last question, if I have time, in the several of your example, you have an initial design. For example, in last example that you showed, how sensitive is your final solution to that remeshing? If I change, sorry, not remeshing, my initial assumption. If I change this, how this change will impact my final solution?
So so it's a classical. It's very known that it is certainly sensitive to the initialization, and because of the computational intensivity of as it was computationally intensive, I did not run many initializations to find the best optimal design. But the idea is that if the problem is sufficiently constrained, then the optimal design will be more and more or less sensitive to initialization. And I mean, I think for the body fit for the heat exchanger, it's certainly dependent on the optimal design, on the initial design, because if you don't give a good topology, you cannot allow mixing of the two fluid parts during during iterations. So if you prescribe just two channels which do not interlace each other, you will never generate a structure that interlace. So in this sense, it matters a bit, but in the level set, in the frame of the level set method, it's always good to, I mean, taking designs with a lot of holes has proved to give rather nice results and not too sensitive to initialization. So
thank you very much. Very cool result. I appreciate your presentation.
Filippo, you have raised your hand, please.
Yes, thank you. I've got two questions, if there is the time. The first one I'd like to ask Florian is, since you're running like large computation, parallel computation, I'd like to have your comments on the time it takes to remesh. Okay, it takes a lot of time.
So it's in 2D, it's almost instantaneous. So in 2D, remeshing is not an issue. In 3D, I must acknowledge that for this kind of nice results, it can take 1 hour to remesh one iteration. And so typically these results took me like 1 or 2 weeks on 30 CPUs. It was something like 10 days. Also, so this remeshing part is the only step which is not achieved in parallel right now. So there are evidence in the literature that shows that we will be in a short future, we will be able to remesh in parallel. But right now, so there is actually already a parallel version of MMG, but this version is not able to deal with the level set discretization yet. And so it's more a matter of people working on this than possibility. So I guess in a coming future, there will be room from improvements for that also to be able to remesh on a large with multiple CPUs.
Okay, thanks. That's great to know. And the quick question I have on this figure, actually, on this fluid-to-fluid heat exchanger, is that you've got 3 phases, right? You've got the warm fluid, the cold fluid, and then you've got the interface. I didn't get if you're using like multiple level set, or if you're using just one level set. How do you distinguish 3 phases?
So the idea, so it's not strictly speaking a level set method where the domain is represented by level set. It's really a body fitted approach. And so I start with a design where the fluid and the solid are explicitly discretized. So it's possible to detect which component, what is the fluid component associated to the hot inlet, and what is the component associated to the cold inlet. Okay. And then from that we can construct a level set for the fluid domain. In fact, yes. So when the fact that we need 2 level sets is needed only in order to impose the distance constraint. But this is purely the computation of the modeling of the distance constraint with a penalty functional and the computation of the derivative of this functional. So this uses the computation of sign distance functions, which are somehow also level set. But in order for the shape updates, we don't need 2 level sets. We need only 1 level set.
Okay. Okay, very interesting. I'll be looking more in details to that work. Thanks.
Thanks.
Let me add one small comment to what Florian said. He's always using the word remeshing. So indeed, it is remeshing, but not remeshing from scratch. I mean, we remesh from the previous mesh, so it takes a lot of time, but less than if you were remeshing from scratch. Or it's just adapt the previous mesh at each iteration.
Yeah, that is correct, and also the remeshing time decreases over the iterations. Yeah.
But the mesh topology may change, so it's really a remeshing. So it's not deforming.
Oh, no, it's remeshing, yes,
Yeah.
but not from scratch. Yeah.
And you don't need any memory, so you're doing steady computations from scratch each iteration. Then, so you don't need to interpolate from previous solution. Okay.
No.
And then maybe one final comment with respect to the question of Amal saying that we don't need to interpolate from one mesh to another. But of course, since the mesh change, I mean, the size of the discretization space change. And so sometimes it's very hard to compare the objective function because it was computed on two different meshes.
That was my comment, Professor Allaire. Exactly. Yeah. So thank you for
compared to a SIMP method or to the classical level set method, where you have always the same finite element mesh in the background. Here you don't, so there is a small discrepancy. Yes. All right. I mean, if there are further questions, I guess on all the four talks, I guess it's a moment to.
Yes.
Your last question.
We have in fact reached our time limit.
Oh, that's the time limit, right?
Yes, we try to start on time and end on time, so people wherever they are in the world can get about with their businesses.
Okay.
Do you have something to say before we wrap it up?
I don't think so. I mean, I first want to thank the four speakers who were right on time and leave some enough time for question. And so maybe there will be further question, and then you can send them by email. And thank you for all the people who listened to this webinar. And thank you to the main organizer, to you, Niels and June.
Thank you very much, Greg.
Thank you. Yeah, thank you for organizing this great session. So in the coming months, we would have a ultra-large scale symposium on ultra-large scale topology optimization. And after that, the WCSMO will take place. So because of these conferences, we will pause this topology optimization webinar. And so we will restart probably in September. So thank you for joining us today, and looking forward to see you in the conference or in topology optimization webinar in the future.
Okay.